Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to learn how to identify intermolecular forces in mixtures, and we're also going to cover physical properties of liquids and solids. We're going to start by reviewing the intermolecular forces that we covered last lecture. Let's begin with dispersion forces. These are the weakest type of intermolecular forces. They're present in all molecules, but they are the dominant force in nonpolar molecules, which are molecules that have no permanent dipole. These forces arise due to temporary fluctuations in electron distribution, which creates a momentary dipole that can induce dipoles in neighboring molecules. The strength of dispersion forces increases with molecular size because larger molecules have more electrons, and that makes their electron clouds easier to distort. Then we have dipole-dipole forces. These are the intermolecular forces that exist between polar molecules. And polar molecules are molecules that have a permanent dipole moment due to differences in electronegativity between their atoms. The greater the difference in electronegativity, the stronger the dipole moment, and therefore the stronger the dipole-dipole interaction. Then finally, we discussed hydrogen bonding. This is a special type of dipole-dipole interaction, but it's much stronger than regular dipole-dipole forces. This force occurs only when hydrogen is directly bonded to nitrogen, oxygen, or fluorine, the three most electronegative elements. Since these elements pull electron density so strongly, the hydrogen atom is left with a significant partial positive charge, and that strongly attracts the lone pairs from nitrogen, oxygen, or fluorine atoms in neighboring molecules. In addition, hydrogen bonding plays a major role in biological systems such as DNA base pairing, and also plays a huge role in physical properties like boiling points, melting points, and so on. Now, in addition, in the previous lecture, we also discussed intramolecular forces like covalent and ionic bonds. As a friendly reminder, I want to mention that for ionic interactions, these are intramolecular and these forces exist between fully charged ions, such as the sodium cation and the chloride anion in sodium chloride, also known as table salt. These ionic interactions are much stronger than any of the intermolecular forces we've discussed so far, and they're also stronger than covalent bonds. Now that we've reviewed these forces, let's move on to how they manifest in mixtures. When we combine substances, the type of intermolecular forces that form between them depends on the intermolecular forces present in each individual component. The key to identifying these interactions is to first determine the dominant intermolecular force in each substance separately, and then analyze how they interact with each other when they're mixed. Let's go through some scenarios. If both molecules are nonpolar, the only intermolecular force between them will be London dispersion forces. Since nonpolar molecules lack permanent dipoles, they rely entirely on temporary induced dipoles to interact. We can also say this is a case of instantaneous dipole forces. For example, if we have nitrogen gas and oxygen gas, they're both nonpolar, and that means they interact only through weak dispersion forces. And since dispersion forces are weak, gases like nitrogen and oxygen gas remain in the gas phase under normal conditions, instead of condensing into a liquid or solid. If both molecules are polar, then here they will experience dipole-dipole interactions, where the partial positive end of one molecule is attracted to the partial negative end of another molecule. Let's take chloromethane as an example. These molecules are polar, meaning they're going to interact through dipole-dipole forces where the partial positive carbon in one molecule is attracted to the partially negative end of another molecule. Then if one molecule is polar and the other is nonpolar, then this interaction is called a dipole-induced dipole force or a dipole instantaneous dipole force. Here, the polar molecule is going to temporarily induce a dipole in the nonpolar molecule, and that's going to allow for that weak attraction between the two. So here we have chloromethane, which is polar, and oxygen gas, which is nonpolar. The permanent dipole in chloromethane is going to induce a dipole in oxygen gas, and that's going to allow for the dipole-induced dipole force. Now, if one molecule is ionic and the other is polar, then the interaction that happens here is called an ion dipole force, which is particularly important in dissolution processes, such as how sodium chloride dissolves in water. The example we have here, however, is sodium chloride in chloromethane. Sodium chloride is an ionic compound. It's made up of sodium cations and chloride anions. The partially negative charge on the chlorine in chloromethane, that's going to be attracted to the sodium cations in sodium chloride. And the partially positive end here in the carbon atom of chloromethane, it's going to be attracted to the chloride anions in sodium chloride. And in this manner, they form ion dipole interactions. If both molecules can form hydrogen bonds, then they're going to experience hydrogen bonding. This is a particularly strong type of dipole-dipole interaction. And this occurs when a hydrogen atom is covalently bonded to a highly electronegative atom, like nitrogen, oxygen, or fluorine. And they're going to be attracted to a lone pair on another electronegative atom. So in this case, if we have two water molecules, they're going to form hydrogen bonds due to the highly electronegative oxygen atom that's pulling electron density away from the hydrogen atoms. And that creates a partially positive hydrogen and a partially negative oxygen. So the partially positive hydrogen of one water molecule is going to be strongly attracted to the partially negative oxygen of another water molecule. And what this results in with a bunch of water molecules is an extensive hydrogen bond network. And this gives water a lot of its unique properties, like its high boiling point, its surface tension, and many more. Finally, if both substances are ionic, they experience ion-ion interactions, which are the strongest of them all. So here we have sodium chloride interacting with sodium chloride. Since both compounds are ionic, they will interact through strong ion-ion electrostatic attractions. Now, taking this all, let's apply what we've learned to a couple of concept check questions. This first question asks, which of the following compounds has ionic forces as the dominant force? To answer this question, we need to identify which of the compounds is ionic. Ionic forces exist between fully charged ions, meaning the compound must consist of a metal and a nonmetal where electrons have been transferred to create positive and negative ions. Our first answer choice is magnesium oxide. This is an ionic compound. Magnesium is a metal and oxygen is a non-metal. Magnesium donates 2 electrons to oxygen, forming magnesium 2 plus cations and oxygen 2 minus anions that are held together by strong electrostatic attractions, which define ionic bonding. This is in fact the correct answer, but we're still going to work through B, C, and D. B and C are hydrogen gas and fluorine gas. These are both nonpolar molecules, meaning they only experience London dispersion forces. And since they consist of identical atoms, there's no dipole and there's no ionic interactions, only dispersion forces. So neither of those are the correct answer. Then finally, we have here carbon tetrachloride. This is also a nonpolar molecular compound, meaning its dominant intermolecular force is also London dispersion forces. It doesn't contain ions, so it cannot have ionic forces. Therefore, it's also not the correct answer. Our final answer for this problem is A. Magnesium oxide is the only compound in this set that exhibits ionic bonding. Our second question says, which of the following compounds has hydrogen bonding as the dominant intermolecular force? To answer this, we need to recall that hydrogen bonding only occurs when hydrogen is directly bonded to nitrogen, oxygen, or fluorine. These 3 elements are highly electronegative, meaning they pull electron density strongly and they create a highly polarized bond where the hydrogen has a significant partial positive charge. And this allows the hydrogen to then interact strongly with the lone pairs on nitrogen, oxygen, or fluorine atoms in neighboring molecules, thereby forming a hydrogen bond. Let's examine each choice. Our first one here, this is methanol. It exhibits hydrogen bonding, and that is because it contains an oxygen-hydrogen bond. And that means the hydrogen bonding is the dominant intermolecular force here. The oxygen has a lone pair that can form hydrogen bonds with hydrogens from neighboring methanol molecules. This is in fact the correct answer. Let's work through the other options as well. So B here, C2H4, this is a nonpolar molecule, meaning it only experiences London dispersion forces. It also has no oxygen-hydrogen, nitrogen-hydrogen, or fluorine-hydrogen bonds, so it cannot exhibit hydrogen bonding. Here for C, this is methane. This is also a nonpolar molecule, so it only experiences London dispersion forces, no hydrogen bonding. And then finally here we have fluoromethane. This is a polar molecule, but the fluorine is not attached to any of the hydrogens. This molecule has a central carbon that's bonded to 3 hydrogens and then a fluorine atom. The fluorine is not directly bonded to any of the hydrogens. Therefore, it only experiences dipole-dipole interactions, but no hydrogen bonding. So it's also not the correct answer. Our final answer here is A. Methanol is the only molecule in this set that exhibits hydrogen bonding. Then our final problem for this concept check is which intermolecular forces are experienced by C2H6. Now, in this molecule, what we have is single bonds between the carbons, and then there are single bonds between 3 hydrogens on each carbon. This molecule is nonpolar, and the only intermolecular forces that are present in nonpolar molecules are London dispersion forces. So that means the correct answer here is A, dispersion only. And with that, we can move into our next topic. Now that we have a solid understanding of intermolecular forces and how they dictate interactions between molecules, we want to shift our focus to the physical properties of liquids. Liquids exhibit a wide range of behaviors based on the strength of their intermolecular forces. And understanding these properties will help explain why different liquids behave the way they do. Why do some evaporate quickly while others slowly? Why do some liquids resist flow while others do not? And why do some liquids form droplets while others spread out? These properties are all governed by the strength and type of intermolecular forces at play. And we're going to break down the key concepts that will help us make these connections. Let's begin with boiling point. The boiling point of a substance is the temperature at which its vapor pressure equals atmospheric pressure, and that allows the liquid to transition into a gas. This means that at the boiling point, molecules have gained enough energy to overcome the attractive intermolecular forces, keeping them in the liquid phase. Since stronger intermolecular forces require more energy to break, substances with stronger intermolecular forces will have higher boiling points. Now, closely related to boiling point is vapor pressure. So we're going to scroll down here to this part so we can talk about vapor pressure. This describes the pressure exerted by gas molecules in equilibrium above a liquid. If intermolecular forces are weak, molecules can escape into the gas phase more easily, leading to a higher vapor pressure. However, in substances with stronger intermolecular forces, molecules are going to struggle to evaporate, resulting in a lower vapor pressure. This relationship explains why volatile substances like acetone evaporate quickly, where substances like glycerol, which have strong hydrogen bonding, evaporate much more slowly. The rate at which a liquid evaporates is referred to as the evaporation rate. And again, this depends on how easily molecules can escape from the liquid surface. Enthalpy of vaporization is another related concept. It refers to the amount of energy required to convert a liquid into a gas. The stronger the intermolecular forces, the more energy is needed to overcome them, meaning that substances with stronger intermolecular forces will have a higher enthalpy of vaporization. Moving on, let's go back here and talk about surface tension. Surface tension is the phenomenon where a liquid surface resists external forces. This resistance arises from cohesive intermolecular forces, which pull molecules at the surface inward and thereby minimizes the surface area. This is why water forms spherical droplets rather than spreading out. It has strong hydrogen bonds that create high surface tension. In contrast, liquids with weaker intermolecular forces are going to spread out more easily, and they're going to have lower surface tension. Another important property influenced by intermolecular forces is capillary action. This describes the ability of a liquid to travel up a narrow tube against gravity. This process occurs due to adhesive forces which cause the liquid to stick to the container walls and cohesive forces which hold the liquid together. If adhesive forces are stronger than cohesive forces, then the liquid will rise along the tube's wall, creating a concave meniscus that you see right here. If cohesive forces dominate, then the liquid pulls inward, forming a convex meniscus like you observe here. Lastly, we want to discuss viscosity. This is a liquid's resistance to flow. This property depends on how strongly molecules interact with each other. Liquids with stronger intermolecular forces flow more slowly because their molecules are tightly held together. In contrast, liquids with weaker intermolecular forces are going to flow more easily. Additionally, molecular shape plays a role. Longer, more entangled molecules are going to experience more resistance to flow, and that further increases their viscosity. Now, intermolecular forces not only dictate the type of interactions that occur between molecules, but also determine key physical properties that influence the behavior of substances in different phases. All of these properties, boiling point, vapor pressure, evaporation rate, enthalpy of vaporization, surface tension, capillary action, and viscosity, are all interconnected through intermolecular forces. And understanding these relationships allow us to predict and explain trends in physical behavior. So to start, let's establish a fundamental rule. As intermolecular force increases, the strength of attraction between molecules also increases. And this leads to a direct impact on several properties that we're going to discuss on this page. So as intermolecular forces increase, all of the physical properties written in orange here will also increase because there is a direct relationship between increasing intermolecular forces and these properties. Let's go over some of them again. So for boiling point, this is going to be directly proportional to the strength of intermolecular force. A substance with strong intermolecular forces are going to require more energy to transition from the liquid phase to the gas phase because molecules must overcome those forces to escape into the vapor phase. This is why water, which exhibits strong hydrogen bonding, has a much higher boiling point than, say, methane, which only experiences weak dispersion forces. Similarly, the enthalpy of vaporization follows the same trend. Substances with stronger intermolecular forces require more energy to vaporize, and that leads to higher enthalpies of vaporization. Viscosity, which is a liquid's resistance to flow, is also directly related to intermolecular forces. The stronger the intermolecular force, the more the molecules tend to stick together, making it more difficult for the liquid to flow. Surface tension follows a similar pattern. This property describes the tendency of a liquid surface to resist external forces, which is a direct result of cohesive forces between molecules. Then there's capillary action. This is the ability of a liquid to move up a narrow tube against gravity. It's another intermolecular force dependent property, and it results from the balance of adhesive forces and cohesive forces. Adhesive forces are the attraction between the liquid and the container surface, and cohesive forces are the attraction between liquid molecules. Stronger intermolecular forces contribute to stronger cohesive forces, which in turn affect how liquids behave in capillary tubes. Now, with all of these properties that we've covered, we've noted that they increase with stronger intermolecular forces. Now we want to cover properties that show an inverse relationship. So as intermolecular forces increase, these properties written in gray are going to decrease. Evaporation rate, for instance, is negatively correlated with intermolecular force strength. If intermolecular forces are weak, molecules can escape into the gas phase more easily, resulting in a faster evaporation rate. This explains why volatile substances like acetone evaporate quickly, whereas water evaporates much more slowly due to its strong hydrogen bonding. Vapor pressure follows a similar trend. Substances with weak intermolecular forces have higher vapor pressures because molecules can readily escape the liquid phase, thereby increasing the number of vapor phase molecules above the liquid. In contrast, substances with strong intermolecular forces are going to have lower vapor pressures because fewer molecules can transition into the gas phase. Finally, the concept of gas ideality is also inversely related to intermolecular force strength. In an ideal gas, molecules are assumed to have negligible intermolecular interactions, meaning that stronger intermolecular forces cause real gases to deviate from ideal gas behavior. Non-ideal gases experience attractions between molecules, which reduces their tendency to expand and behave according to the ideal gas law. This is why gases like water vapor, which can form hydrogen bonds, exhibit deviations away from the ideal gas law, whereas noble gases like helium, which only experience weak dispersion forces, behave much closer to an ideal gas. Now that we've established these relationships, let's discuss a useful strategy for ranking intermolecular forces in different substances, and then we're going to jump into a couple of practice problems. For this part, I want to show you the following diagram here that we're going to use to learn how to rank intermolecular forces in different substances. This approach is called the bucket method, and here our first step is to categorize substances into four major groups: non-polar molecules, polar molecules, hydrogen bonding molecules, and ionic compounds. Non-polar molecules, they experience only London dispersion forces, so they have the weakest intermolecular forces. Next are polar molecules, which experience dipole-dipole interactions. They have stronger forces than nonpolar molecules, but they're weaker than hydrogen bonding molecules. Molecules that exhibit hydrogen bonding, they fall into the next category, as hydrogen bonding is significantly stronger than regular dipole-dipole interactions. And finally, we have ionic compounds, which involve full charges rather than partial dipoles, so they experience the strongest forces due to electrostatic attractions between oppositely charged ions. Then within each category, we can further refine rankings based on molecular properties. So for non-polar molecules, the strength of the dispersion forces increases with molecular weight. So the strength of dispersion forces increases with molecular weight because larger molecules have more polarizable electron clouds. Then for polar molecules, the strength of the dipole-dipole interaction depends on the difference in electronegativity between atoms in the molecule. Then for hydrogen bonding, This follows a specific ranking that we covered in the previous lecture that we need to have memorized. All right, ammonia is weaker than hydrofluoric acid, and hydrofluoric acid is weaker than water. And then finally, for ionic compounds, the intermolecular force strength increases as charge density increases, meaning smaller, highly charged ions exhibit the strongest electrostatic interactions. So here you want to spend some time going over the rules we covered for lattice energy to help you rank ionic compounds. Now that we have covered intermolecular forces, how to determine the present intermolecular forces in mixtures and how to rank them, as well as physical properties for liquids, let's jump into a couple of practice problems. This first one says, which best defines the vapor pressure of a liquid? A says pressure of the vapor above the surface of liquid in a closed container. B says pressure of the liquid when it's open to air. C says pressure of the liquid when it's in a closed container. And D says pressure of the air above the liquid surface area. Now recall that vapor pressure refers to the pressure exerted by gas molecules in equilibrium above the surface of a liquid in a closed container. And this occurs because some molecules at the surface of the liquid gain enough energy to overcome intermolecular forces and enter the gas phase. So looking at the answer choices, option A correctly states that vapor pressure is the pressure of the vapor above the liquid surface in a closed container. So A is the correct answer. Next, we have a problem that asks, which is predicted to have the lowest adhesion? Adhesion refers to the attraction between molecules of a liquid and the surface of another substance, such as a container or a solid material. Strong adhesion allows liquids to stick to surfaces. However, substances with weak intermolecular forces, they're going to exhibit lower adhesion because their molecules do not strongly interact with other materials. So we are looking for which of these has the lowest adhesion. In essence, we're looking for which of these options has the weakest intermolecular force, since intermolecular force and adhesion are directly related. What we notice right off the bat is that all of these options are nonpolar, which means they all just experience London dispersion forces. Then it becomes a matter of figuring out which of these answers have the weakest London dispersion forces. This is directly related to molecular weight. The smaller the molecule, the lower or the weaker the London dispersion forces. The bigger the molecule, the stronger the London dispersion forces. Out of these options, neon is going to be the smallest, so it's going to experience the weakest London dispersion forces, meaning it has the lowest adhesion. The correct answer is A. Finally, this last problem here says which of the following substance is expected to have the highest evaporation rate. Evaporation rate is inversely related to intermolecular force strength. Substances with weaker intermolecular forces evaporate more easily because their molecules require less energy to escape into the gas phase. So keeping that in mind, let's evaluate each option. A is methanol. This exhibits hydrogen bonding due to the OH bond. So that means it has strong intermolecular forces and a relatively low evaporation rate. Then we have bromine. This is a large nonpolar molecule that experiences only London dispersion forces. Now there's another option here that's also a nonpolar molecule that only experiences very weak London dispersion forces, and that's going to be fluorine. Hydrogen sulfide is polar, and it experiences dipole-dipole interactions, which are stronger than dispersion forces, but weaker than hydrogen bonding. Ultimately, our goal is to figure out which of these has the highest evaporation rate, so the weakest intermolecular force. So we have a tie here in terms of just a general assignment of intermolecular forces. Both bromine and fluorine have very weak London dispersion forces, but which one is weaker? Because the weaker dispersion force is going to result in the highest evaporation rate. To determine that, we need to compare their sizes. A smaller nonpolar molecule will have weaker dispersion forces than a larger nonpolar molecule. And here, fluorine is going to be smaller than bromine. So fluorine has the highest evaporation rate, and the correct answer is D. With that, we move into our final topic for this lecture, which is all about solids. Solids can be classified into 4 main types based on the nature of their bonding and structure. We have ionic solids, metallic solids, molecular solids, and covalent network solids. The type of bonding within a solid directly affects its physical properties, including melting point, hardness, and conductivity. One of the most straightforward ways to classify a solid is by recognizing the types of elements in the compound. Ionic solids are typically composed of a metal and a nonmetal, forming an ionic bond through electron transfer. In these solids, positively charged metal cations and negatively charged nonmetal anions are held together by strong electrostatic forces, also known as ionic bonds. Because ionic bonds involve full charges rather than partial charges, they create a highly stable lattice structure, which requires a significant amount of energy to break apart. This explains why ionic solids generally have high melting points. The melting point of an ionic solid, of course, depends on charge density. Higher charges and smaller ionic radii result in stronger electrostatic attractions, and that leads to even higher melting points. For example, sodium chloride and magnesium oxide, they are both ionic solids. But magnesium oxide has a much higher melting point than sodium chloride because magnesium oxide has a greater charge on the magnesium cation than the sodium cation, and same goes for the anions. Now, unlike ionic solids, metallic solids are made entirely of metal atoms, and they can be identified pretty easily by their element composition. If a solid consists of only one type of metal or an alloy, it's classified as a metallic solid. These solids exhibit metallic bonding in which valence electrons are delocalized and free to move throughout the structure, essentially forming a sea of electrons. This delocalization is also responsible for the high electrical and thermal conductivity of metals, as well as their malleability and ductility. Since metallic bonds vary in strength depending on the metal, the melting points of metallic solids can actually range from low to high. For example, mercury, it's a liquid at room temperature, while tungsten, this is a solid, and it has one of the highest melting points of any element. Now let's consider molecular solids. So unlike ionic and metallic solids, which involve strong intramolecular forces, ionic or metallic bonds respectively, Molecular solids are held together only by intermolecular forces. These forces include London dispersion forces, dipole-dipole interactions, and hydrogen bonding, depending on the molecules involved. Because intermolecular forces are much weaker than ionic or covalent bonds, molecular solids, they tend to have low melting points and they're often pretty soft. For example, solid carbon dioxide, also known as dry ice, it goes under sublimation directly into a gas at negative 78.5 degrees Celsius because it is held together only by weak dispersion forces. Finally, we can discuss covalent network solids. They are at the extreme end of the spectrum in terms of bond strength. These solids, they consist of a continuous network of atoms covalently bonded to each other, forming this extended and very rigid structure. So unlike molecular solids, which rely on weak intermolecular forces, covalent network solids, they have strong directional covalent bonds throughout the entire structure, and that makes them exceptionally hard, and it gives them really high, extremely high melting points. Common examples include diamond, which is just a network of carbon atoms, and silicon dioxide, which is also known as quartz. Because covalent bonds require a large amount of energy to break, these solids typically have the highest melting points of any solid type. So to summarize, the strength of bonding within a solid directly influences its melting point. Molecular solids have the lowest melting points because they are held together by weak intermolecular forces. Ionic solids have higher melting points with their strength depending on charge density. Metallic solids also can vary widely in melting point depending on the strength of metallic bonding. And then covalent network solids, they typically have the highest melting points because breaking them requires disrupting an entire network of covalent bonds. Now that we understand how to classify solids and we understand their relative melting points, let's go ahead and apply this knowledge in tackling a couple of practice problems. The first one asks, what type of solid is silver chloride? To determine this, we recognize that silver is a metal and chlorine is a nonmetal, and this combination indicates ionic bonding. So silver chloride is an ionic solid, and the correct answer here is C. Our final problem for the lecture asks, which of the following compounds has the highest melting point? We have ammonia, hydrofluoric acid, lithium fluoride, and fluorine. Now, out of the options here, lithium fluoride is an ionic solid, while the others are molecular solids. An ionic solid is going to have the highest melting point in this set, so the correct answer is C. And with that, we've completed this lecture. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.